Video 2.9 is about motion on an inclined plane. In figure A to the right, we see a motion diagram of an object sliding down a straight, frictionless inclined plane. Note that the angle of the incline is shown as theta on the drawing, and the velocity vector is getting larger after each frame, and the acceleration vector points in the same direction as the velocity vector, agreeing with the fact that the sled is the object is speeding up as it goes down the incline. In the second figure, we see the free fall acceleration, a vector free fall, that the object would have if the incline suddenly vanished. It's pointing straight down towards the center of the Earth, which would be the reason for its acceleration. We can break this vector, a free fall, into two components, a vector parallel and a vector perpendicular. The surface somehow blocks the perpendicular component, so the one-dimensional acceleration along the incline is given by a sub s, where a is the acceleration in the s direction, equal to plus or minus g times the sine of theta. Now let's try to understand where this relationship a sub s is equal to g sine theta comes from. We see that theta, shown here, is also indicated as the angle between the perpendicular component and the a free fall vector. How do we know that that's true? Well, it agrees with a rule from geometry. If you have angle 1, which has one side perpendicular to a side of angle 2, and has its second side perpendicular to the second side of angle 2, then those two angles are the same. So if we believe that, then we're looking at the angle theta between the perpendicular component and the free fall component, free fall vector, we see that the sine of theta is equal to the opposite side, a parallel, over the hypotenuse, a free fall, which in this case is g. So if the sine of theta is equal to a parallel over g, where a parallel is equal to a sub s, then a sub s is equal to g sine theta. And the sign of a sub s can be positive or negative, depending on the direction that the ramp is tilted. Note that this is a constant acceleration as the object slides down the incline, so the four kinematic equations for constant acceleration will apply. So let's apply what we just, the things that we learned from the previous slide in this problem 2.26. In this problem, a skier is sliding along at 3 meters per second on a horizontally frictionless snow. He suddenly starts down a 10-degree incline. His speed at the bottom, we're told, is 15 meters per second. We're asked to find two things. What is the length of the incline, and how long will it take him to reach the bottom? Here I have written out the problem, 2.26, on a sketch pad. And I show at the bottom here on the left a motion diagram of what's happening in the problem. We see at the top 3 frames are shown as the motion is horizontal, and the velocity vector is the same because the skier has a constant velocity during this point. And then the skier starts down the hill, and the velocity vector gets bigger with each frame. The total distance from the top of the hill to the bottom of the hill along the direction of the path I've labeled as L. And L is one of the unknowns that we're asked to find in this problem. Next, I show a breakdown of the acceleration vector acting on the object as it's going down the incline. And I show that a sub s, as we saw in the previous slide, 2 slides ago, is equal to g sine theta. So what do we know when we tackle this problem? Well, we know the initial speed is 3.0 meters per second along the s direction, and his final speed is 15 meters per second. And actually, we only know this to 2 significant figures, so this is a mistake. The acceleration, we know, is equal to g sine theta, since the acceleration is in the in the s direction and is pointing towards increase in s. So we say that it's plus g sine theta, where g is 9.8 to 2 significant figures, and theta is 10 degrees. So and then we're supposed to find the length of its travel, or the distance that it travels down the incline, delta L, which we'll call delta S for the displacement in S, and the time interval for the trip down the incline, delta T. Well, this is motion of an object with an acceleration that is constant. So we use one of our 4 kinematic equations for constant acceleration. In part A of the problem, we want to find a displacement, and we know what the final velocity is and what the initial velocity is. So we can use our equation 3, which states that v final in the s direction squared is equal to v initial in the s direction squared plus 2 times the acceleration times the displacement in s. We want to find out what the displacement in s is. So we solve for that. Delta s is equal to v final squared minus v initial squared over 2 times the acceleration Then we put in the numbers. So we have 15 meters per second squared minus 3.0 meters per second squared over 2 times the acceleration, which is 9.8 times the sine of 10 degrees. And when you do this calculation with your calculator, be sure that you have your calculator set to degrees and not radians. So now let me plug these numbers into my calculator. And when I do that, I see that the distance the skier travels down the incline is 63 meters. Now in part B, we're asked, what is the time interval for the trip down the incline? Well, I know what the final velocity is, and I know what the initial velocity is, and I know what the acceleration is. So I can use my first kinematical equation. V final, the s direction, is equal to v initial, plus the acceleration times the time interval delta t. So this means that delta t is equal to v final s minus v initial s over a sub s, which is equal to v final minus v initial over g sine theta. So if we put in the numbers, that's 15 minus 3.0 meters per second over 9.8 sine 10 degrees meters per second squared. And by the way, I left off my units above. Let's look at that for a second. Meters per second squared. So that meant in my calculation for the displacement that in the numerator we had meters squared per second squared, and the denominator we had meters per second squared. So the second squareds cancel out, and we end up with meters. And this calculation now for delta t, we're going to have meters per second in the numerator, meters per second squared in the denominator. The meters will cancel out, and we'll end up with seconds in our answer. So now let me go to my calculator. And when I do that, I get an answer of 7.05 seconds, which the two significant figures is 7.1 seconds. I hope you followed my procedure here, and please email me if you have some question. In this quick check, the ball rolls up the ramp, then back down, which is the correct acceleration graph. Well, as the ball goes up the ramp, it has an acceleration that points in the opposite direction as the direction of the velocity vector. So midway, the ball feels an acceleration due to gravity, has a component of acceleration equal to g pointing down the incline, vertically downward, and has a component of that is pointing down the incline, and this acceleration is equal to minus g sine theta. Why minus? Well, if s is in this direction, then the acceleration vector is pointing in the opposite direction as increasing s. So it is has a negative sign. Now you might ask, what about when it comes briefly to a stop and then starts to roll back down? When it stops, does its acceleration go to 0? The answer is no. That acceleration is still minus g sine theta, even at the top, and even as its velocity has gone to 0. Just as when you throw a ball in the air and it reaches its maximum height, and that instant its velocity is 0, its acceleration is still equal to minus g. So the correct answer in this quick check is answer D. And that concludes this video.